Okay, so in this video, I'm going to continue talking on section 5.2 series, and I want to do a couple more examples on the sequence of partial sums, on using the sequence of partial sums to find the sum of a series. So remember, what we do is we take the infinity and we change it to k, and we let that vary. So we do S1, which is just the sum from 1 to 1 of negative 1 to the n. So the only n I'm plugging in is 1. So that's just negative 1. And then S2 is the sum from n equals 1 to n equals 2 of negative 1 to the n. So that's negative 1 to the 1 plus negative 1 to the 2. So that's negative 1 plus 1, which is 0. And then S3, right, is the sum from 1 to 3 of negative 1 to the n. So that's negative 1 to the 1 plus negative 1 to the 2 plus negative 1 to the 3. So that's negative 1 plus 1 and another negative 1. So that becomes negative 1. And then if we do S4, right, we get the sum from 1 to 4 of negative 1 to the n. So we have the first 4 terms, right? We plug in n equals 1, n equals 2, and finally n equals 4. So it's negative 1 plus 1 minus 1 plus 1, so we end up at 0. So we see that we go from negative 1 to 0, negative 1 to 0, and it's safe to assume that this pattern will repeat itself because, right, when we raise negative 1 to an odd power, we get negative 1 out. When we raise negative 1 to an even power, we get positive 1 out. So this pattern surely will continue. So therefore, when we think about what's the sequence of partial sums, right, Sk is negative 1, and then it goes to 0, and then negative 1, and then it goes to 0, and then negative 1, and then 0, and so on and so forth, forever like that. So if we think about the limit as k goes to infinity of Sk, right, we see that we're oscillating between 0 and negative 1. So it's never going to converge. So therefore, Sk diverges. So then we get that this limit here also diverges. Right, so that means that its sum is not a real finite value that we could determine. Alrighty, so let's do one more. So let's try to find the sum from 1 to infinity of 1 over n times n plus 1. Right, so right now the only tool we have in our toolbox for finding the sum of a series is to generate the sequence of partial sums and see what the limit of that sequence is. So my partial sums, remember, I'm going to take and I'm going to change that infinite bound to a finite bound k. Then I'm going to evaluate for different values of k. Right, so first I'll start with S1, which is just the sum from 1 to 1 of 1 over n times n plus 1. So this becomes 1 over 1 times 1 plus 1. So that's just 1 over 2. Right, and then S2, right, that's going to be the sum from 1 to 2 of 1 over n times n plus 1. So the first term I know is a half, and then I'm going to add in, plugging in 2. So that's going to be 2 times 3 is 1/6. And then a half, right, that's the same thing as 3/6. So this is equals to 4/6, right, or 2/3. And then S3 is the sum from 1 to 3 of 1 over n times n plus 1. Right, and we already saw the first term is a half, the second term is a sixth, and then I need to plug in 3 to get my third term. So 3 plus 1 is 4, times 3 is 12, so this becomes 1/2 plus 1/6 plus 1/12. Right, and we already know that these is 2/3, so that's 8/12, so this is 9/12 or 3/4. Right, so then if we try and do S4, right, that's the sum from 1 to 4 of 1 over n times n plus 1. Right, so let's bring down all of our first 3 terms that we already figured out. And then we have to plug in 4 to figure out, our fourth term. So 4 plus 1 is 5, times 4 is 20. So this is going to become 1/2 plus 1/6 plus 1/12 plus 1/20. And that's going to be 4/5. All right. So right now for SK, the whole sequence of partial sums, right? The first partial sum, the first term in the sequence is 1/2. The second term, S2, is 2/3. The third one is 3 over 4. Fourth one is 4 over 5, and that'll go on forever. So, right, remember, we want to find a formula between the index and, the term that we're on, right? So, I like to write them out like this when we're trying to figure out a formula for the sequence. And then notice that the numerator of each of these fractions matches the index. And then the denominator is just one greater than that. So remember, you always try to find a relationship between the value of the term and the index of the term that you're on. So we can write a formula for SK as, right, K, right, so the numerator matches the subscript. That's what we observed. And then the denominator is just one above the numerator. And then we can take, remember, we want to take the limit of the sequence of partial sums. So if we take the limit of that, right, remember that if the power is the same, we can just use the coefficients of the variable. So here there's an imaginary 1, imaginary 1. So this is just 1 over 1, which is just 1. Right, so that means that our series converges. And we know that its sum is equals to 1. Okay, so hopefully that clarifies. Remember, what you want to do is create a sequence of partial sums and then take the limit of that sequence. And that the answer of that limit is going to inform what the actual series is converging to. Thank you. Bye-bye.